Okay, so on with chapter 10, which is thermal physics. Now, we're going to talk a lot about temperature in this chapter, and the effects of temperature and how we describe temperature. Temperature is just a description of an object's energy, thermal energy in this case. An object with more energy, that is thermal energy, has a higher temperature. We have to define a few terms first. When I talk about thermal contact, it just means that two objects are touching such that energy can be transferred between them. Two or more objects are touching. So that energy can be transferred between them. And then thermal equilibrium occurs when objects are in thermal contact, but they're not exchanging energy. So they're able to exchange energy, but they're not. We would say they're at the same temperature. And notice that with thermal contact, it doesn't mean necessarily that they're touching. Like I can have two objects that are not touching, but say they're connected by, I don't know, a thermally conductive strip, a piece of metal or whatever, that can transfer energy from one to the other. So we would say that those objects are in thermal contact. Zeroth Law of Thermodynamics says if objects A and B are separately in thermal equilibrium, with a third object C. So for example, let's say I have an object A here, I have an object B here, and they're in thermal equilibrium with an object C. Right, such that they're the same temperature. If they're in thermal equilibrium, that means that they have the same temperature. So there's no energy flowing from one object to the other. Then, if that's true, if objects A and B are separately in thermal equilibrium, then they're also in equilibrium with each other. This is called the zeroth law of thermodynamics. We might get to the first and second, we'll see. But the zeroth law just says this, that if A is in equilibrium with C and B is in equilibrium with C, then A is also in equilibrium with B. Let's say, for example, let's say C has a temperature of 270 Kelvin. That would mean A has a temperature of 270 Kelvin, 270, 270. And so A and B would equally have the same thermal energy, or the same temperature. Now, when we talk about heat, heat is the exchange of thermal energy. So for example, these two objects are in thermal contact. What would be the direction of the heat or energy transfer? Well, the energy transfer is going to occur from the hot object to the cooler object. So we would have heat or energy transfer that would go from the wood to the lead, the wood having a much higher temperature. Now, we have a number of different ways to measure temperature, a number of different thermometers. and temperature scales. Um, for different types of thermometers, you can measure temperature by looking at physical quantities of other materials. So for example, the volume of a liquid. This is our good old standby mercury thermometer, or an alcohol thermometer, whatever the object is. So we have a tube, it has a bulb at the bottom, it's filled with say alcohol, which is usually dyed red. And then as this heats up, the alcohol will expand its volume up to the appropriate temperature, and it's calibrated. So this is measures the temperature based on the volume of a liquid. We can also find a temperature based on the length of a solid. Right? This is like your old thermostats in your house. We'll talk about that a little bit later. A thermostat in your house on your air conditioner, though many of yours don't use that anymore, but they used to use the length of a solid, the length of a metal. You can measure the volume of a gas at constant pressure. I know from the ideal gas law, which we'll get into on this, that PV is equal to nRT. So if T changes and if pressure is constant, then V is going to change. The pressure of a gas at constant volume so in a similar way, except now we're saying we have constant volume, and if the temperatures change, the pressure is going to change. Electric resistance of a conductor. This is called, I have a number of different names for these, thermocouples, thermistors, thermometers. Their electrical properties change as their temperature changes. So for example, with a thermistor, it's like a resistor, but it's thermally sensitive. So when the temperature changes, the resistance of that device changes. You can also look at the color of a very hot object. We do this with stars. So for example, a blue star is a lot hotter than, say, a red star. Now, there are a number of different scales that we use. We'll talk about 3 different scales: the Celsius temperature scale, the Fahrenheit scale, and the Kelvin scale. And you'll need to know how to, what those scales are based on, and then how to convert from one scale to another. So the Celsius temperature scale is based on the freezing and boiling points of water. So they say that with the Celsius scale, the freezing point is equal to 0 degrees Celsius, and the boiling point is equal to 100 degrees Celsius. This is just set. I say that this is the freezing point down here on our Celsius scale, and this is our boiling point, and there are 100 degrees between that. So there are 100 marks between the freezing and boiling point, and that's how we set the Celsius scale. The Fahrenheit scale is set very similarly. It's based on the boiling and freezing points of water as well. But obviously they have different values attached, where the boiling point or the freezing point is 32 degrees Fahrenheit. This is my freezing point. And 212 degrees Fahrenheit is my boiling point. It's a little more cumbersome scale, which is why most of the world don't use the Fahrenheit scale anymore. It's cumbersome because you have this really odd numbers that are chosen for the boiling and freezing points of water. So we have 32 and 212, and there are 180 degrees between the boiling and freezing point. So that's the size of the degree. So notice that the size of the Celsius degree, a change in 1 degree Celsius, is quite a bit bigger than a change in 1 degree Fahrenheit. Just sort of a good rough idea to have is that a room temperature of 70 degrees Fahrenheit is about 20 degrees Celsius. So that's a good idea to have. But remembering also that a change in 1 degree Celsius is a lot bigger than a change in 1 degree Fahrenheit, more than twice as big, or almost twice as big, rather. This is how we convert from one to the other. It's just based on the number of degrees between them. You could probably derive it on your own. But the Fahrenheit temperature is equal to 9/5 the Celsius temperature plus 32. Let's look at the third scale, which is the Kelvin scale. The Kelvin scale, which is the SI unit for temperature, but we'll often use the Celsius scale, or they also call it centigrade. The Kelvin scale is based on absolute zero and the triple point of water. And the triple point of water. And absolute zero is the lowest temperature attainable, the lowest possible temperature. It is that theoretical temperature where all motion ceases, all intermolecular motions, electrons, protons moving, those all stop. It's the lowest possible temperature. It's not possible to go lower than absolute zero. And at absolute zero, this absolute zero of 0 Kelvin, the pressure is equal to 0 pascals, which is a perfect vacuum. There's nothing there. And nothing is moving. So the vibrations of subatomic particles will cause a temperature greater than 0 Kelvin. So it's really a theoretical temperature. And then to convert between Kelvin and and then it's also based on the triple point of water. Sorry, the triple point of water is the point where water exists as a solid, liquid, and gas. It's a particular pressure and temperature where you have this water, solid, liquid, and gas. And it occurs at the temperature for the triple point is equal to 273.16 Kelvin, which in the centigrade scale is 0.01 degrees Celsius. So just above the freezing point of water at a particular pressure and at this particular temperature, you get, under certain conditions, the existence of solid, liquid, and gas water all in one time. So the Kelvin scale is based on T equals 0, which is absolute 0, to T equal 273.16, which is the triple point of water. So we have between absolute 0 and the freezing point of water, basically we have 273 degrees. Okay, so to convert between the Kelvin and Celsius scales, we do this. We say that Celsius temperature is equal to the Kelvin temperature minus 273.15. So for example, absolute 0, which is the absolute lowest temperature, is equal to negative 273.15 degrees Celsius. Right. One thing when we write Kelvin temperatures, they're not measured in degrees in the same way, so we don't use the degree sign. We just list the units. All right, there is a quick test here, I believe, which you can find. Just converting 20 degrees Celsius to kelvins. You can pick that up on your own, and we'll